Right, so here we are going to do section 3.7, improper integrals, and we're going to throw in a little practice of L'Hopital's rule at the end. So far, all the definite integrals, or the integrals that have bounds that we've done so far, have a finite answer and a finite limit of integration. Everything has just been an area or a volume, something really kind of tangible. So now we're going to try to think about a little bit of a what if game. So let's first imagine the graph of f of x equals 1 over x squared, which I'll graph here for us, give or take. This is the graph of y equals 1 over x squared. So the idea here is I want to think now about the area underneath the curve from 1 to b. So from 1 to some ending point. So let's think about that ending point here. I'm going to kind of make that a little smoother maybe because it wasn't the greatest picture. Here's the x value of 1, and then I'm going to end at somewhere else. So this is the area that I'm going to be looking for. Easy enough to calculate. It'll be an easy one. We'll actually do the calculus for that. That's not so bad. The real question is what happens if b gets a little bit bigger? And then I'm looking for this area, or even a little bit bigger, and I'm looking for this area. And so what happens as b gets bigger and bigger and bigger? That's sort of our end goal question here. So let's go through and do the actual calculus. I think it's going to be not so bad. So we'll start off with the integral from 1 to b of 1 over x squared dx, which we know can turn into the integral from 1 to b of x to the negative 2 dx. Sometimes that negative exponent is a little bit easier to calculate the antiderivative, add 1 to the power, divide by the new power. And then I'm going to simplify it first and then plug in the bounds. Maybe you plug in the bounds first and then simplify. Doesn't really matter too much. So this is negative 1 over x evaluated from 1 to b, which becomes negative 1 over b minus negative 1 over 1. And of course, 1 over 1 is 1, and two negatives turn into a positive. So I end up with negative 1 over b plus 1. Okay, easy enough. So like, for example, let's do a little what if game here, right? So if, let's say, b was 2, then that would mean the integral from 1 to 2 of 1 over x squared dx without having to redo the work. We certainly don't need to redo it. We've already got it once over here on the left. We certainly don't need to do it again. It would just be negative 1 over 2 plus 1, which was 1/2. So like if b was, let's say, 10, a little bit larger, then it would become the integral from 1 to 10 of 1 over x squared dx, which would be negative 1/10 plus 1. So 9/10 is what that would be. And if it were, you can kind of imagine, let's say if b were 100 even, then it would become the integral from 1 to 100 of 1 over x squared dx, negative 1 over 100 plus 1, or 99 over 100. And perhaps you can imagine what might happen as b is getting bigger and bigger and bigger. Rather than redoing all the work, I'm just kind of plugging in the larger number for b. As b is going bigger and bigger and bigger, it looks like that final value, the answer to those integrals, ended up getting closer and closer to 1. So we have a notation for that and a vocabulary for it. So let's write that down. It's called an improper integral. So an improper integral, it's called that because, let's say, our bound is not finite. That's one reason why this could be an improper integral. Another reason is straight from the picture. The picture is also infinite, right? That's maybe another way that I could describe an improper integral. So the integral from 1 to infinity of 1 over x squared dx is equal to, here's the huge notation. You can't just say b is equal to infinity. It's impossible to equal infinity. Infinity is not a number. So you have to be really careful. So you have to actually use the limit notation. It's the limit as b approaches infinity from 1 to b of 1 over x squared dx. Without the limit notation, you might get a right answer, but all of the meanings would be lost. And so really, we don't care about the answer. We care about the meaning. Math is a language where you don't care about the last page of the book. We care about the whole book. So the notation is really, really important. And then we can go through and do the work again. But since we already did it above, I'm not going to redo the work again because I already did the work for the integral of 1 over b, or sorry, the integral from 1 to b of 1 over x squared. I already did that. And I ended up with negative 1 over b plus 1. And then I can take that limit, and now it becomes a Calc 1 question. I've done the integral already. Now this is a Calc 1 question all by itself. This is just a limit of a function. And as b goes to infinity, 1 is 1. And then you can think of 1 over a really large number approaches 0. Does it ever get to 0? No, but it gets closer and closer. So we say its limit is equal to 0. Okay, and then of course 0 plus 1 is equal to 1. So we say that the improper integral, I'm going to label this correctly, the improper integral, the integral from 1 to infinity of 1 over x squared dx converges. We use the word converges because it had a finite answer at the end of the limit. Not only does it converges to the number 1. So it converges to 1 is how we say that. That's like the final answer to this question. Okay, so now we have an idea of what an improper integral is. There's other types of improper integrals that we want to focus on as well. So perhaps we could be thinking about going to negative infinity. If that were the case, that would be another improper integral. It could have gone to a positive infinity like we did before. And if you have the integral from a to infinity, you do have to turn that infinity into a limit because you cannot plug in infinity. Infinity is not a number. Similarly, with negative infinity, if you had a bound of negative infinity, you had to turn that into a limit because you can't plug in infinity. And similarly for both of them, if you have both the positive and negative, then you have two different limits, and you can break up that integral somewhere in the middle. And that somewhere in the middle is whatever number it is. It doesn't necessarily matter what number that c is because f is continuous, so that didn't matter. All right, and then if we say if the limit exists, the improper integral is said to converge. Okay. Meaning it has a numerical solution, right? And it's said to converge to whatever that numerical value is. If the limit does not exist, then the improper integral is said to diverge. It's the vocabulary term there. So those are definitely the two new vocabulary terms. Converge and diverge are vocabulary terms that we are going to use a whole lot the rest of the semester, very, very frequently. So make sure we're comfortable with those vocabulary terms. Okay, we've got all of our definitions. Let's practice a little bit. The integral from 1 to infinity of dx over x plus 1 cubed. I'm going to go ahead and notice, first of all, it's an improper integral because I have an infinite bound. And so then I have to, step 1, you have to turn that into a limit. It's the limit as b goes to infinity from 1 to b of x plus 1 to the negative 3 dx. Then I can do the integral. I'm going to draw a parentheses here. Now, you don't have to draw that parentheses if you don't want to, but technically it is there. Technically, there are those parentheses right around the integral. And then if you think about order of operations, you do the integral first and the limit later. So that order of operations is quite important, which is why the parentheses might be helpful to you. So the limit as b goes to infinity. Now I'm going to do that integral. This is linear on the inside, so I can add 1 to the power, divide by the new power. Don't forget to also divide by the constant multiple. It's just that my constant multiple was 1 in this case, so it wasn't necessary. Evaluated from 1 to b. And then I'm going to do the same thing I did before, which was simplify first and then plug in my bounds. You're welcome to plug in your bounds first and then simplify. It doesn't matter which order you do that. You are eventually going to have to simplify, so I like to start right at the beginning. So negative 1 over 2 times x plus 1 squared evaluated from 1 to b. Keep the limit notation. Without that limit notation, the equal signs would be wrong. Each equal sign you write down has to be correct. So then I have still the limit as b goes to infinity. And I still have that limit because I'm still working inside these parentheses. I'm not done with inside the parentheses yet. That's why I still have that limit notation. So negative 1 over 2 times b plus 1 squared minus a negative 1 over 2 times 1 plus 1 squared. And you can see there how the two negatives canceled, and that's why that turned into a positive. And then I could simplify right now if I want, that would be fine, or I could simplify it later as well. We got lots of options. So negative 1 over 2 times b plus 1 squared plus 1 over 8. Okay, so I'm kind of done with the integral now. There's no other integration calculus that I can do. So now I can do the limit part of the calculus. This is now a Calc 1 type of question. 1/8 is just 1/8, so I can ignore that. And as b approaches infinity, so you should think of a really large number, a million, a billion, something large. I tend to think in my head of a million. Obviously, that's not super large, but it feels large, so it helps me visualize it. So 1 over a really large number, a million. $1, a million friends, you're all broke. That guy goes to 0. That 2 didn't necessarily matter. So then, of course, the answer to the limit is 1/8. And we would then say that the improper integral converges. Not only does it converge, it converges to 1/8, which is really kind of a fascinating thing. I want to scroll back up and look at the previous picture. What we did in that previous problem where we had that the integral converges to 1, we saw this picture, this infinite object. It really did go on and on and on and on and on and on and on forever. It never ended, has an area of 1, which I think is really interesting. Now, does it ever reach that area at the end? Well, no, I can't ever finish graphing it, but its area does settle down and it converges. So it settles down to that number of 1, which I think is really cool to think about. Same thing for this part, this next example there that we found, where it converges to 1/8. I didn't draw the picture there, but we found an area that converges to 1/8, an infinite object that settled down to an area of 1/8. Okay, let's do another one. So same thing, this is improper integral, so you have to turn that into a limit notation. The limit as b goes to infinity. I just use the letters A and B because it's a habit of mine. You can use any letter that you want that's not already a part of this integral. It just has to be different. So if this was a dA, then I would not be able to use the letter A, but it's a dx, so I can use anything that's not x. So that's the only requirement on that letter choice, e to the negative 2x dx. Then I can do the antiderivative. This becomes the limit as b goes to infinity. The antiderivative of e to the negative 2x is e to the negative 2x divided by negative 2. Don't forget your limit notation along the way. The limit as b goes to infinity. E to the negative 2b divided by negative 2 minus e to the negative 2 times 0 over negative 2. And now I'm going to simplify. I simplified it in a different order than before. That's okay. 1 over negative 2e to the positive 2b. Negative exponents brought down to the bottom. 2 negatives cancel. E to the 0 is 1. And then I take the limit as b approaches infinity. So again, 1 over e to the million becomes 1 over a really large number, which goes to 0. So my answer here was 1/2. This integral also converges. If you get a real number, it converges. If you get does not exist, or if you get infinity or negative infinity, then it diverges. Let's practice another example. Okay, so let's practice one more. The integral from 1 to infinity of cosine, same type of question. The limit as b goes to infinity of the integral from 1 to b of cosine. Keep track of your limit notation. Antiderivative of cosine is sine. So then I have the limit as b goes to infinity of sine of b minus sine of 1, and then I take the limit as b goes to infinity, and what does sine of b approach? Well, you know the graph of sine of x, right? Yeah, never settles down. So that truly just simply does not exist because it never settles down. It's 1, 0, negative 1, 1, 0, negative 1. It never settles down. So then in this case, that's an example of an integral that diverges. All right, we're doing good. Let's do another one. This next one, I might run out of space when I think I'm gonna try to squeeze it in here. It's a little bit of a longer one, but we can do it. The integral from 2 to infinity of cosine of pi over x all over x squared dx. So just like before, because it's an improper integral, you have to turn it into a limit. And then I have cosine of, it is pi over x. I'm just choosing to write it as pi times x to the negative 1 for no real reason other than I just think it's a little bit smoother for myself to write it down that way. And then I'm going to do an integral because remember there are technically a set of parentheses right here. So you're doing inside those parentheses first, following order of operations. So the integral has to come first. So here is another example of where I'm going to need a u sub. Now that we've made it this far in our integration techniques, at this point, it's free game. I could do u sub, integration by parts, trig identities, trig substitution, partial fractions. Anything is fair game now. So all of the integration strategies, we still have to know all of those and keep practicing those. If I were to let my u be pi x, excuse me, to the -1, then du is negative pi x to the -2 dx. And then that would mean that du divided by negative pi is x to the -2 dx. I think I'll highlight this just so everybody can see it. That 1 over x squared dx is now going to turn into the du over negative pi. And then we can go from here. So then this is going to become the limit as b approaches infinity of, I don't need that parentheses, though I certainly can put it, the integral of, it looks like cosine of u du over negative pi. So this is great. Negative pi is just a constant. We'll come back to that later. That part doesn't matter, but there's kind of a really big deal right here that I want to point out. You cannot have bounds on an integral equal no bounds. This is not true. What you see on the screen right now is not true. I've written down something that is completely incorrect. So we have to be careful. Everything you write down has to be a true equal sign. So you really have to think this is has bounds. This one does not. So it's not a true equal sign. Basically what I mean to say is every single time you change your variable, make sure you change your bounds. So here I did a u sub, I should change my bounds. My variable is now different. It was x, now it's u. Similarly to when we did trig sub and it was x and then it was theta. If you change your variable, you have to change your bounds. So let me go back in and do that. So u of 2 would just be pi times 2 to the -1 or pi over 2. And then u of, b would be, there we go, pi over b. So my bounds are now pi over 2 and pi over b. Okay, all right, I'm going to give you guys a second to catch up while I give myself some space. Okay, so now we're going to keep integrating. We got this. Don't forget to keep track of your equal sign and your limit notation. The limit is still there. And then the antiderivative of cosine is sine, so that's not so bad. So sine of u. But I still have that negative pi as a constant multiple on the bottom, so it's still there. And then evaluated from pi over 2 to pi over b. And then this is going to become the limit as b approaches infinity of sine of pi over b over negative pi minus a sine of pi over 2 over negative pi. Sine of pi over 2 is 1, so I can replace that. That'll be easy enough. And then sine of pi over b, I'm taking the limit as b approaches infinity. So inside that parentheses, that fraction pi over a really large number goes to 0, and then sine of 0 is just 0. And then minus 1 over negative pi, so I now have 1 over pi. This is another example of an improper integral that converges. Ta-da! All right, let's do a little bit more. The next thing that we're going to talk about is a family of functions. We're going to try to figure out what happens with an entire group of functions, not just one function at a time, an entire group or a family of functions. So think of the very first one we did today, which was 1 over x squared. I'm going to do 1 over x squared, but I'm also going to do 1 over x cubed and 1 over x to the 4th and 1 over x to the 1/2 and 1 over x to the 2/3 and maybe 1 over x to the -5, all of them. So where p is just some real number. Okay, so I'm going to do all that entire family of functions, and we are in this case going to integrate it from 1 to infinity. So there's my improper integral. And the question is, for what values of p, that power, will this integral converge? For what values of p will that integral converge? So let's go and think it through one at a time. I'm going to start off with just writing out what I have. the integral from 1 to infinity, I'm going to write, excuse me, right away as a limit. The limit as b approaches infinity. Okay, and then I'm going to do instead of writing it as 1 over x to the p, I'm going to write it as x to the negative p. Okay, and then I'm going to do the antiderivative. So I still have a limit. So this becomes the limit as b approaches infinity. If I'm going to add 1 to the power, divide by the new power. I add 1 to the power and divide by the new power, evaluate it from 1 to b. This becomes the limit as b approaches infinity of b to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. Okay, and I'm going to simplify that. That's going to become the limit as b goes to infinity of b to the negative p plus 1 over negative p plus 1 minus 1 to the power of a number. Remember, p was a number. So 1 to the power of a number just becomes 1 over negative p plus 1. And I might as well distribute that negative across to simplify my life a little bit. So that would become then a positive 1 over p minus 1. Cool. Okay, that's not so bad. I'm trying to take the limit though. So this is where we have to do a little bit of a what if situation. So we are going to do a little what if. I'm going to do just a couple of what ifs in a row, and then I'll do a third one later on. So it's going to take up a little bit of space though. I'm going to do first, what if I'm going to make up a number. And you might not want to write this down. You might want to just watch for a second. This one's going to be tricky. I hope we have everything up to here written down. But for right now, just watch. I'm just going to make up a number 2. 2 is a good number. What happens if p were 2? Okay, if p were 2, I'm not going to redo all that work. That's crazy. Let me just look at the very end, that last line of that calculation. If p, the power, were 2, then this exponent would become negative 2 plus 1, which is a negative number. It's a negative number. That exponent would be a negative number. If that's the case, then the exponent is a negative number. It really just is a negative number. That's all I'm trying to say there. Now, what happens when you have an exponent as a negative number? If the exponent is negative, then this entire thing, b to the power of a negative exponent, becomes 1 over b, right? That's how negative exponents work. So that would become 1 over a really large number. So that would go to 0. Okay, let me think about it again. Still don't write it down quite yet. Just watch. I'm just going to change the number. We're doing it all in our head for a minute, a little bit of yoga for the brain. What if p were 5? Okay, if p were 5, then that exponent, is it still negative? It is. Then it's a negative number there. If that's the case, then same thing with that exponent being negative, then this would flip upside down and this whole thing would go to 0. So now this is what I do want you to write down. We kind of have a little bit of an idea. Think about it now as if p were bigger than 1. This is now what you do want to write down. If p is bigger than 1, then negative p plus 1 is still a negative number. So that exponent is still a negative number. If that were the case, then this whole thing would go to the bottom of the fraction, which as I take the limit as b goes to infinity would go to 0. All right, let's write that down. This would become the limit as b approaches infinity of b to the negative p plus 1 over negative p plus 1 over p minus 1. And I'm going to circle some stuff I recommend you do as well. I'm going to circle that whole exponent, and it's going to be a negative number. And because I have b to the power of a negative number, then that's going to be a 1 over b. As b goes to infinity, that goes to 0, which means that this integral would converge to 1 on p minus 1. Cool. Okay, that was a good what if scenario. Let's do another what if scenario. Let's do another what if scenario. So I'm going to now think about it if P were less than 1. Think about it like if P were 0. Maybe just watch for a second too. If P were 0, then this exponent negative P plus 1 would become a positive number. If P was 0, that exponent is positive. And if the exponent is positive, I don't flip the fraction. This would just become infinitely large to the power of 1, which is just infinitely large. That would diverge. If P was -5, for example, -5, think of it in your head as -5, then this would become a -5 plus 1, which is +6. So if P were a less than 1, then that exponent is a positive number. Right? Then it's a positive number. Then that would mean that the limit as b goes to infinity of b to the negative p plus 1 over negative p plus 1 plus 1 over p minus 1. This exponent is a positive number. So that whole thing would then approach infinitely large. And that would mean, since that limit was infinity, that would mean that the improper integral would diverges, where it got converges when I had a finite number. All right, we're doing really good. We thought of a couple scenarios. We thought of if P was bigger than 1, and then we thought about if P is less than 1. What we haven't thought about is if P is equal to 1. If P is equal to 1, then this entire thing falls apart. You can't divide by 0. Yeah, we cannot divide by 0. If P is equal to 1, all that work falls apart. All right, so I got to start from scratch for P is equal to 1, which we can definitely do. I'm going to give myself a little bit of space for this, so I apologize for that break in the visual. Okay, let's now start from scratch if P is equal to 1. All that work I did before falls apart because I cannot divide by 0. So if P is equal to 1, all of that work is completely wasted. So meaning I just have to start from scratch. I can't say it diverges. I have no idea. Maybe it does, maybe it doesn't. I have no idea. I cannot say anything because I can't divide by 0. That doesn't give me converge or diverge. That gives me, oh no. So you have to start over again, okay? So I'm going to have now, it's the integral from 1 to infinity, which I've turned into the limit notation of 1 over x to the p, but in this case, p is 1. Oh, this is an integral we actually just know. So I don't have to divide by 0, obviously. So this becomes the limit as b goes to infinity of ln of x, evaluated from 1 to b, the limit as b goes to infinity of ln of b minus ln of 1. Ln of 1 is 0, and ln of a really large number approaches a really large number, so it happens to also diverge. So the only time we got converges is if P was bigger than 1. So that's our conclusion. We need to write down a conclusion sentence. We have to conclude all of this. There's not a single answer to this problem. That's not how these problems work. Math is a language. You're telling a story now. You are not finding an answer. An answer is really, truly, genuinely not the point. So we got to stop thinking about finding a single answer. We are now telling a whole story. So here is my whole story on the screen right now. My conclusion to this story is that the integral from 1 to infinity of 1 over x to the power of p dx converges if p was bigger than 1, and it diverges if p was less than or equal to 1. That's the conclusion. There's not like an answer to circle. There's a lot of stuff on the screen, I know, because that's the whole story. We told the entire story. We have a conclusion to that whole work. Ta-da! All right. Let's do another example. All right, so now we have a little bit more. Find the volume of the solid generated when the region bounded by f of x equals x squared plus 1 to the power of -1/2 and the x-axis on the interval from 2 to infinity is revolved around the x-axis. So just like we did in chapter 2, when you're trying to find the volume of anything, draw a picture. Step 1 is to draw the picture. It's not a perfect picture, but I use my graphing calculator and it looks a little something like that. I'll try to make it more symmetric. It does happen to be symmetric, but there is my function f of x, and I'm looking for this from 2 all the way off to infinity, and then I'm going to find the volume of the solid when this guy is revolved around the x-axis. So I'll choose my regular sliver or my dx sliver, and if I revolve that around, you can see how that created a disk. So this is the disk method. So for the disk method or washer method, it's volume equals pi times the integral of the big R squared minus little r squared. I don't have a little r because I have no hole in the graph. So I only have the big R squared, which is x squared plus 1 to the negative 1/2 squared. That was my big R squared, evaluated from 2 to infinity. And so then I would have pi times the limit as b approaches infinity of the integral from 2 to b. This simplified as 1 over x squared plus 1 because that square root would have gone away. And then I do the integral. You're welcome to do the trig sub here. This is a classic trig sub problem. You would let your x equal 1 tangent of theta. You would go through and do that work. I encourage you to pause the video and practice the trig sub right now. And then this becomes the limit as b approaches infinity of, and it turns into tangent inverse of x evaluated from 2 to b, which now I have pi times the limit as b goes to infinity of tangent inverse of b minus tangent inverse of 2. And then maybe I need a quick little reminder of what tangent inverse looks like. My guess is a lot of us forgot. This is the graph of tangent inverse. It has asymptotes. This is at y equals pi over 2 and y equals negative pi over 2. This is my arc tangent of x function. Hopefully you remember that from a trig class. But either way, that means that as b approaches infinity, this guy approaches pi over 2. So my final answer was pi times pi over 2 minus tangent inverse of 2. And so this volume converges because I got a finite number. Units cubed because we found a volume. Ta-da! All right, excellent, excellent. Let's do another real similar idea. I'm going to set this one up. I won't go through and solve the whole thing. Find the volume of the solid again generated when the graph of this function and the x-axis on the interval from 2 to infinity is revolved around the x-axis. It's actually very similar. The graph itself is a little bit different, but here's my 2 to infinity of the function revolved around the x-axis. It's the same thing. I'm going to do the washer disk method. So volume is pi times the integral from 2 to infinity of 1 over the square root of x times ln of x squared dx. You would end up having to simplify it first. I'll give you a little hint. You are going to need a u sub. You would have to let your u be ln of x. Try practicing that one on your own. Try to see if you can pause the video right now and finish the answer to this one on your own. I got a final answer of pi over ln of 2. Cool. Okay, we do have one more type of improper integral. So there's a lot of improper integrals. I know there's one more type. We're going to think about for this particular one, yeah, this is just a typo. Sorry, let me fix that function. I didn't give you the function. I meant to give you the function. I'm going to think of that function, sorry, as 1 over the square root of x. I don't know why I didn't give you the function. I apologize. Okay, but we're going to graph it. We're going to graph the integrand and then evaluate this integral. So my integrand, I'll graph my function 1 over the square root of x. This is the function 1 over the square root of x. And then I'm graphing this from 0 to 1. So really this is the area that I'm looking for. You should be able to see that that's actually infinite, right? Or unbounded. But it's not unbounded in the bounds. It's unbounded in the integrand. So that's what we mean by an unbounded integrand. Even though you don't see the infinity symbol written down, it is still infinite. So this does still count as an improper integral. And what makes it improper? If I went from, ooh, sorry about that. If I were to go, let's say from 1/2 to 1, this would not be improper because nothing would be infinite. It's totally bounded and settled and ta-da. So it's this actual 0 in the bounds of my integral that made this completely unbounded. Okay, so all that to say, the integral from 0 to 1 of 1 over the square root of x dx, it's the 0 that is the problem point. Well, first of all, you can't divide by 0. But 0 is what made this picture unbounded. So it's the 0 that is the problem. So it's the 0 that has to change into a limit. I'm just going to choose the letter A. You could still choose letter B if you want. I promise you, it doesn't matter. Just pick a letter you haven't already used for the problem. So the limit as A approaches 0, but we got to be really careful. Look at the picture. This is where the picture is really going to matter. I'm actually on the right side of 0 only. I never went to the left side. So this is actually a one-sided limit. The limit as A approaches 0 from the right-hand side of 1 over the square root of x dx. And then I keep going. So then I have that limit notation. Don't lose your limit notation. I can add 1 to the power, divide by the new power. Dividing by 1/2 is the same thing as multiplying by 1. This becomes the limit as A approaches 0 from the right-hand side of 2 times 1 to the 1/2, which you know is just 1, and then minus 2 times A to the 1/2, which you know is the square root of A. And then as A approaches 0, that guy will also approach 0. So this guy here approaches 0. So the answer is 2, and it does, in fact, converge. Ta-da! So sometimes you can't tell it's improper unless you graph it. So really, truly, you gotta graph them. You can't just assume that I don't need a limit. You might need a limit now. You have to go with the picture to see if you're going to need a limit. Is it improper or not? Is it bounded or not? Okay, so this is the other piece of improper integrals. This is the unbounded integrands, where it's possible that the function itself is shooting up to infinity, just like what I had on that previous graph. And if that's the case, then you're going to need to turn the problem point into a limit. So I'm going to highlight a couple of things. If A is what's making my function go to infinitely large, then A is what has to change and turn into a limit. Okay, let me say that again. You might want to watch, maybe just watch for a second. If B is what is making my function go to infinity, then B is what has to change and turn into a limit. Okay. And it's possible you have to break a single integral up into 2 different integrals as well. We'll do an example. And then, of course, if the limit exists, it's said to converge. If the limit does not exist, or if the limit is infinity or negative infinity, then the improper integral is said to diverge. Okay, let's practice some more examples. So evaluate this integral. Now I have the integral from 0 to 8 of dx over the cubed root of x. This is a great problem because it looks way too easy. It looks like you want to just do an integral right away, right? I don't blame you. But you have to notice there's a problem. I cannot evaluate this as it's written. It is impossible because I cannot divide by 0. That is a problem. So even though you don't see infinity as the symbol, you could draw the graph of this function 1 over the cubed root of x, and you would then see that the function shot up to infinity. So this is an improper integral, which means I have to include the limit. So I have the limit. Now 0 was the problem point, so it's what needs to change. I just chose letter A. You can choose letter B or Q or happy face. It doesn't matter, I promise. Of 1 over x cubed root of x dx. And then you have to remember that A is approaching 0, but I'm only on the right-hand side of 0 because I'm looking at the numbers between 0 and 8, which are all on the right-hand side of 0. Okay, now you can do the calculus. Don't forget to do the integral first and then the limit later. So to do the integral, I'm going to add 1 to the power, divide by the new power. And then this will become the limit as a approaches 0 from the right-hand side of 3 over 2 8 to the power of 2/3 minus 3 over 2a to the power of 2/3. And then I'm going to continue on. We're just trying to simplify along the way. I'm going to simplify this first and then do the limit. It's just something to help you guys practice how to simplify this. So the limit as a approaches 0 from the right-hand side, you can type that into your calculator if you'd like, but it is 8 to the 2/3. So the cubed root of 8 is 2, and then squared is 4 times 3 is 12, divided by 2 is 6. There we go. Minus 3 over 2a to the power of 2/3. And then I'm going to take that limit, and this guy, obviously 0 to the power of 2/3 is just 0. So my answer there was 6, and that integral converges. Ta-da. I know, I've done a lot that converge. I think I only did like 2 of them that diverged. So sorry. Sometimes they converge, sometimes they diverge. You don't really know until you try. Let's do another one. Let's do another one. The next one, the integral from 1 to 11 of dx over x minus 3 to the 2/3. Now, you might look at this and just try to integrate it right now as it is, and I don't blame you. But there's a bit of a problem with this one. There's definitely a bit of a problem. And the main problem with this one is even though 1 is okay to plug in and 11 is okay to plug in, the number that is not okay to plug in is 3. 3, and if you could graph this if you'd like, and you would see that I would have a vertical asymptote at x equals 3. You should also just notice that I can't plug in 3. You should also notice that, but graphing it is always a guarantee. And 3 is inside the interval in question. So this is, in fact, an improper integral. This really, truly is an improper integral. So that's a bit of a problem. So the only way I can turn it into a limit is the limit has to be for the problem point. So this would become the integral from 1 to 3 of x minus 3 to the 2/3 dx, and then plus the integral from 3 to 11 of x minus 3 to the negative 2/3 dx. Sorry, I'll give you some space there so you can see it at least. Yeah. And then each one of them is going to turn into a limit. So then I do the limit as, let's say, b approaches 3 from the left-hand side of the integral from 1 to b of x minus 3 to the negative 2/3 dx plus the limit. Now I'm just going to use a different letter as a approaches 3, and that one's only from the right-hand side, from a to 11 of x minus 3 to the negative 2/3 dx. Then I can do the calculus. Keep simplifying. We got it. And then I can take the limit at the very end. Just make sure that you're nice and careful. Practice with your notation. Keep track of your limits. But each one of those limits just so happen to be 0 in this case. You know that's not always going to be the case. Sometimes it ends up being infinity, let's say. But I ended up with just -3. Sorry, I don't know why I changed the color. I ended up with -3 times -2 to the 1/3 plus 3 times 8 to the 1/3. Feel free to simplify or get a decimal. Ta-da. Sometimes that will end up diverging, though. It does happen. It's very, very possible that you can have an example that diverges. So I'm going to give you another example. I'm going to skip that secant one for now. It's not particularly challenging. I'm going to give you a different example really quick. Let's do an example, let's say from negative infinity to 1 of 1 over the cubed root of x dx. This is definitely an improper integral, so the limit doesn't really matter what letter I choose, as a goes to negative infinity of the integral from a to 1, sorry, from a to 1 of x to the negative 1/3 dx. I can do the integration first. The limit as a approaches negative infinity of x to the power of 2/3, I had to think about it, sorry, 2/3 times 3/2, add 1 to the power, divide by the new power from a to 1. The limit as a approaches negative infinity of 3/2 times 1 minus 3/2 times a to the 2/3. And here is an example where as a approaches infinity, this guy shoots off to infinity. It's not a negative exponent or anything like that. So this answer to the limit was infinite. So therefore that integral diverges. All right, we're doing good. I have one more example that I want to do. This is kind of the trickier one. This will require the most algebra. The calculus for this one is definitely not so hard, but really focus on paying attention to practicing the algebra, including the Calc 1 when we are going to end up needing some tricks for the limits. The calculus itself, even the antiderivative, I should say itself, isn't too bad, but it's good to get the practice. So here's an example of one where even though you don't see the infinity, this is in fact unbounded, because you could graph it if you'd like. It's not particularly exciting, but instead of graphing the whole thing, I'm just going to graph, just to remind you really quick what ln of x looks like, just in case you forgot. So the graph of ln of x looks a little something like this. The reason why I'm bringing that up is so that you can see that as x approaches 0, ln is in fact unbounded. Well, either way, or you should remember to not plug in 0 into a log. That's another thing that you should know. But here we have it. It's definitely going to be an improper integral. So I have the limit as a approaches 0 from the right-hand side of the integral from a to 1/4 of x times ln of 4x dx. You can think about trying to do a u sub. I always like to think about u sub first because sometimes that's easier, but u sub would not work here. All of the powers there are the same. I don't know this antiderivative off the top of my head. I should try an integration by parts because I've got that product. And remember, when you're trying integration by parts, you still have to think of Liate first. So logs, and then inverse trig, and then algebraic, and then trig, and then exponential. So if you have a log, that has to be your u equals. It's non-negotiable. I do have a log, so I have no choice. I have to let my u be ln of 4x, which means your dv has to be the other one, so x dx. Then you do a du. The derivative of ln is 1/4x times 4. And then I do the antiderivative of the other one. We can do it. There's going to be a lot of work for this one. It's going to take up a lot of space. The integral, actually, let's do this. Sorry. It's uv minus the integral of v times du. That's the formula for integration by parts. And so let me fill in what I have. My u is ln of 4x. My v is x squared over 2 minus the integral of x squared over 2 times 1/4x times 4 dx. And all of that is evaluated from a to 1/4. Okay, we'll simplify this. Before I plug in my bounds, I'm actually going to do the simplification. So I'm going to leave it as x squared over 2 times ln of 4x minus the integral of, hopefully you notice the 4 is canceled and one of the x is canceled. So I have a 1/2 x. And then when I do that antiderivative, you know that will become a 1/2 x squared over 2. So that really is just a 1/4 x squared. Okay, all right, evaluated from a to 1/4. So I'll plug in my bounds. This will become the limit as a approaches 0 from the right-hand side. When I plug in my bounds, plugging in 1/4 is going to give me 1/32 ln of 1. Yep, minus 1/64. I was just typing it into my calculator. Minus, if I plug in a, I got a squared over 2 ln of 4a minus a squared over 4. Then I'll keep simplifying. I'm going to do the limit here. I promise I'm just going to simplify a little bit along the way. Oops, sorry. What happened? What happened? There we go. Ln of 1 is 0, so I'm going to rewrite this now. So now I have negative 1/64 minus the limit as a approaches 0 from the right-hand side of a squared over 2 ln of 4a plus the limit as a approaches 0 from the right-hand side of a squared over 4. I distributed the negative and I distributed the limit. Okay, there we go. There we go. The reason I did it that way is because it looks like that last limit at the end is really easy because 0 squared is just 0. This limit is harder because ln of 0 is undefined. So I got to do some work for that one, which we can do. So negative 1 over 64 minus, that 1/2 is just a constant. So I'm going to bring it on the outside of that limit because it's just a constant. I'll deal with that 1/2 later. I will. And then you might notice that this is an a squared times ln, and the ln graph went down to infinity. This guy is 0. So 0 times infinity is an indeterminate form. You have to turn it into a fraction so that you can use L'Hopital's rule. So ln of 4a over a to the negative 2. And then now I should realize that if I were to graph that ln as a approaches 0 goes to infinity, and a to the negative 2, if I were to graph that, also goes to infinity. So I have infinity over infinity. So I can do L'Hopital's rule, which is oftentimes called Bernoulli's rule. Both are fine. Whichever way is fine. So negative 1 over 64 minus 1/2 the limit as a approaches 0 from the right-hand side. I do the derivative of the top, and then I do the derivative of the bottom, negative 2a to the negative 3. Cool, cool, cool. All right, then I just simplify from there. So negative 1 over 64 minus 1/2 the limit as a approaches 0 from the right-hand side of 1 over a over negative 2 over a cubed, which of course I can simplify even farther. Maybe you do that in your head. Maybe you show the work. Doesn't matter. 1 over a times a cubed over negative 2. So one of those a's canceled, and then I still ended up with, funnily enough, 0 squared. Who'd have thunk? But either way, I still went to 0. So my final answer is negative 1 over 64 converges. Ta-da! 3.7 is a little bit more challenging. Keep practicing over and over again. You might notice as you're working on your 3.7 stuff, you are actually practicing all of the other integration strategies as well. Integration by parts, trig sub, partial fractions, u sub, all of the integration strategies are also being practiced here. So if you didn't feel comfortable with any of the previous content, maybe go back and watch some of those additional videos to get you an extra idea of how to solve these tricky integration problems. Awesome. All right. That's all there is for 3.7. Thank you.